Okay, boys and girls, the stage has been set. So this is the big time. We're now going to investigate the sum of W of n as n goes to infinity. And we'll be putting that sum inside absolute value marks, which means we sum up all the W's, and then we look at the radius r of the result, the distance that that value is from the origin in the complex plane. And when we're adding complex numbers, we can think about that as sort of like vector addition, right? So here's W of 1, W of 2, W of 3. And we're going to put the vectors that point to those places end to end, like this. So there's W of 2 being added to W of 1. And then we can add W of 3 to that. And there's the sum of all three. That's where it's located on the plane. So then we're looking at the radius of that point, right? That red line there. Okay. So the paper states that eventually, as n gets big, that value needs to be less than m, which is some real number, times n to the alpha, for alpha in the region between 1/2 and 1. We just need m to exist, right? Doesn't matter how big it is. But it needs to exist for all alpha. So one value of m needs to work for no matter what alpha is. And what is alpha here? Well, it's a number in the range from 1/2 to 1. And that's sort of like saying 1/2 plus epsilon, right? Which we saw in the Landau hypothesis. The closer that alpha gets to 1/2, the harder it is for us, to prove that this is true. So we think of it being as, just slightly bigger than 1/2. Now, you might remark that this thing about it being less than m times that is a different criteria than the one that the Landau hypothesis uses, right? But actually, it's not as different as it looks at first. Let's go back to Landau for a minute. The Landau hypothesis says that the absolute value of the sum over n to the 1/2 plus epsilon has to go to 0. But we're saying it just needs to be less than n, or less than m, right? Um, but because we have to prove that for any value of epsilon or for any value of alpha, it's going to amount to pretty much the same thing. So let's put Sky's W of n here instead of the lambda function. And let's say that we're, investigating this for some particular value of epsilon. Let's select 1% as an example value for epsilon. So that means we're dividing by n to the 0.51 at the moment. If we have a proof that these all go to 0, then we would have the Landau, criteria met. We'd have Sky's criteria met as well. But what if we only have a proof that they're less than some constant? Well, if that's been proven for any value of epsilon, we can just pivot to a smaller epsilon instead of 1%. So let's look at 0.5%, say. So now we have n to the 0.505. So the limit of that sum over n to the 0.505 is less than m. So let's move n over to the right. And that sum is going to be less than m times n to the 0.505. And then what we're going to do next is divide each side of the equation by n to the 0.51. That's the value that we were originally investigating. So this all now is less than m times the ratio of these two powers of n, right? And we can combine those. And that works out to m over n to the 0.005. Now, let's notice what's happening here. M is a constant. It's not changing. So as n grows, even though that power is very small, the part on the right is actually going to 0, right? N to the 0.005 is eventually going to be so much bigger than m that the right-hand side here goes to 0. And so we have what we want, right? And you can always do that. There's always some lower value of epsilon than the one that you're concerned with, or there's always some value of alpha that's closer to 1/2. So actually, this thing that this guy's paper is stating that we want to prove is basically an equivalent criteria to the one used by Landau. It just kind of states it in a slightly more forgiving form. If we can meet this as like the minimum standard, then we can always make that comparison between different values of alpha and observe that we actually have the stronger form of the statement as well. So this is actually quite close to what the Landau hypothesis is looking for. Okay. So now the first step in our proof is to define some constants that we're going to be using. These values will depend on n, so they're not really constants except when you're talking about a single value of n, but for a while that's what we'll be doing. First one is j. J is basically n to the alpha, except we need that to be an integer, so we're going to use the floor function. That's what those marks are around n to the alpha. That basically just means, you drop the decimal part and you use the biggest integer that's less than or equal to n to the alpha. Then we have this funny thing. We just want k to be n to the 1 minus alpha, but the constraint here is that k and j are both integers and their product has to be less than or equal to n. We're not allowed to round up. So that's why the definition of k looks the way that it does. This is all maybe a little confusing, but here's a summary. So j is close to n to the alpha. K is close to n to the 1 minus alpha, and therefore j times k, if we add those exponents, is close to n. The reason we're not just using equal signs here is first, we need them to be integers. And second, we need to make sure that jk is never greater than n. So that means we can't just round them to the nearest integer, because rounding up is not allowed. We're going to be working with j and k a lot, so take a moment, let's get clear on these definitions. And as an example, if alpha is 0.51, then you might get something like this. But just bear in mind that even though these values look like they're pretty close, j is basically 0% of n when n is really big. And in spite of all appearances, k is going to become something like 0% of j, because that slight difference in the exponent makes a bigger and bigger difference as n grows. So now we have j times k being, maybe just a bit less than n. And if you divide n by j, you get k plus, presumably, some small remainder. And we'll call that remainder r sub n. This is just, integer division, just like you did in grade school. And since Rn is the remainder, it's necessarily less than j. So we have 0 is less than or equal to Rn is less than j. Why do all this? Well, the way the proof is set up, we want to be working with a number of points that's equal to exactly j times k. So we're just going to bracket those extra Rn points, and we're going to treat them separately. And that's a much smaller value than j times k. If we go back to what we want to prove, we can observe here that breaking that sum into two pieces and then proving it separately for each piece is fine. We can just cut this into parts A and B, let's say. And if we find a value of m that works for part A and a different value of m that works for part B, then we could just add those values of m together and get a final m to complete the proof. No problem. So we'll deal with Rn first, since that's easier. Let's look at the sum of the first Rn points. We're thinking about vector addition. We know that those points will partly offset each other, right? But actually, Rn is so small that we don't even need that to happen. We can just write that the absolute value of the sum is less than or equal to the sum of the absolute values. And each of those are 1, right? Because every point W of n has a radius of 1. That's the absolute value. So this expression is equal to Rn itself. But the way Rn was defined, we know that it's less than j, which is less than or equal to n to the alpha. So for this little part, an m value of 1 will suffice. Okay, Rn points easily converge for n to the alpha. So we're done with that part. That works. Okay, so now having squared away the easy part, we now have exactly j times k points, which is a much bigger set of points. For the moment, n is fixed. We've discarded the first Rn points. We have exactly j times k points on the unit circle. And the first thing we're going to do is we're actually going to set aside the information about which integers get us to which point. And we're just going to sort those points instead by their location, right? Which means sorting them by theta, the angle that defines their position. So that means we're going to start near theta equals 0, and we're just going to go clockwise, or counterclockwise around the circle. And having sorted those values, looking at the arguments now, not e to the I theta, but just the theta values, we're going to define theta sub j and k as a way of referring to those arguments. So we're ranging the theta values by size. You could think of this as maybe like a big j times k matrix of theta values. Theta sub 1, 1 is the smallest. Theta sub 1, 2 is next, all the way out to theta sub 1k. And then we increment j, yada, yada, yada. And the very last one is theta sub capital J, capital K, which is those two values that we just defined. And when we do this, let's notice that as we go along, we increment k first while j stays the same. Okay, that's the convention that we're using. Let's zoom in. We're going to zoom way in, because it's the really big values of n that we need to be thinking about, right? The first k points are all going to have a value of 1 for j, right? So when j is 1, that's those first k points. And then the next k points will have a j value of 2, and so on. So we have something that looks sort of like this. So we've rewritten our sum of w's. We've expressed the w of n as e to the I theta with j and k as subscripts. And we have the sum of all of them, first over k and then over j. And then what Sky does here is he swaps the summations. See that? So what does that accomplish? Well, we're still summing all the same things here, but we're summing them up now in a different order than we were at first. So let's look just inside this part for a given value of k. Maybe k is, 17 or whatever. Now we have a sum over j of all the points with theta sub jk. So now j is varying and k is staying the same. So if you scratch your head over this for a little bit, you'll find that, for example, for k equals 17, this is like the 17th point in each group of k consecutive points. So we have 1 point in here, 1 point in there, and so on. So we group them first into consecutive groups of k points. And then now we have each sum using exactly one of those points from each group. And we can sort of think of that as like, maybe a representative value from that group, from each of the j regions. And there are, of course, k of these sums. And because they each have a representative point from each of those little regions, we could sort of expect that the k sums are like roughly equal to each other, maybe. Like that's not a mathematical statement, just kind of an intuitive observation on my part. And now Sky is going to say, look, let's consider the size of each of these k sums individually. One of these sums is the biggest, and there are k of them. So let's just pick out the biggest one. And we can write that collection of sums is less than k times the biggest of them, because there are k of them, and one of them is the biggest. So in this new expression, we don't actually need the subscript k anymore. Okay, we can redefine our thetas now just in terms of j, because k is going to remain the same in this new expression. We have capital K times the sum over the e to the I theta j's, with it being understood that k is whatever value maximized that sum. So let's pause and take stock. We have j times k points, and that sum is less than or equal to k times a sum of j points, where the j points are selected in a way that makes them more or less representative of the overall distribution of points, right? So let's ask the question, what can we say about that distribution? We have a set of points that was originally 1 out of every k consecutive points. Well, if we recall what we proved in video 6, we know that eventually n gets big enough that for any epsilon-sized interval, there are at least n to the x points in that interval. And clearly n to the x can be bigger than k, because k is less than n to the 1/2. So if we know that there are more than k points in any arbitrarily sized interval, that means that the space between these representative points, which is exactly the space that some set of k consecutive points takes up, is less than that interval size. And it was an arbitrary interval. No matter how small of an interval we select, there's going to be an n big enough that intervals of that size will have n to the x points. So even though we're only looking at every kth point from the original set, we have these remaining points actually getting dense on the unit circle as n grows. Neat, huh? So all the circle fills in with these points. Okay, back to our sum. Theta, as discussed, is now only indexed by j, and we're multiplying by capital K, as explained. Next, we're going to multiply this by 2 pi over j. So what is the significance of multiplying by 2 pi over j? Well, let's return for a moment to what we're trying to prove. Multiplying by 2 pi is fine, right? Because we just want to show the existence of m. And m can be any number. So multiplying by a constant doesn't matter. But j is different because j varies for n, right? This is a very deliberate change. J is approximately equal to n to the alpha. So by dividing by that number, we have essentially rearranged our target result like this. We have n to the alpha on the far right. We divide by that. And now we're talking about an expression that we would need to show is less than some constant, m. Okay? And next we're going to do something real weird. We have these representative values. It's not all the WNs, but they're pretty dense, just the same. And we have a sum of all of them. And now we're going to reorder them again in such a way that we have exactly the same sum, but the new list is going to travel around the unit circle in the same counterclockwise direction, not once, but k times. And we want to use one representative out of every k of the remaining points as we go. So like if k was 5, we would take every fifth value, here, all the way around. And then we're going to do a second loop, and we're going to take the ones right after those. Here, all the way around a second time. And by the time we do that 5 times, then we're done. And we've traversed the circle 5 times around. Well, instead of 5 times, it's k times, which is going to be much bigger. How do we do that? Can we do that? And what is that going to mean? Well, class for today is about to end, so we're going to hold some of those questions for the next video. But before we end, let's briefly talk about why we would do that. And just for FYI, okay, I'm stepping away from proving things, and I'm just giving a little preview of where we're going. If we do this, we will have a list of thetas that spans a much larger range. They're no longer going from 0 to 2 pi. Now they're going from 0 to k times 2 pi. Now k times 2 pi is going to infinity as n rises, but that's okay because j, the number of points in our list, is going to infinity a whole lot faster than that. And so eventually, even though we're spreading the points out over a much wider range from 0 to k2 pi, the points are going to fill in. And they're going to become dense even on that expanded range everywhere. And then we have something very interesting. We have a sum of j w of n's multiplied by k2 pi over j. That is a very interesting number because k times 2 pi is the length of the whole range of our values of theta, and j is the number of points that we have in that range. Total distance divided by number of points. That is the average distance between 2 points, isn't it? And now if we think back to our early calculus days, there's this thing that we learned about called a Riemann sum. Stop me if you've heard this one before. You sum a whole lot of sample values of some function f of x, and you multiply each one by a delta of x, the tiny space between itself and the next sample. And as the number of sample points goes to infinity, and delta x goes to 0, the limit of that expression is what? That's the definition of an integral. Okay, so looking at this guy here, we have what appears to maybe be a Riemann sum whose limit would be the integral of the function e to the I theta d theta over values of theta ranging from 0 to k2 pi. And that's just k times around the unit circle. So that integral, well, it's going to be equal to k times the integral once around the circle from 0 to 2 pi. And that's a very simple and very well-known result in complex analysis. Boys and girls, that integral is definitionally equal to 0. Whoa. Okay, so I've skipped a few details to get us here. But this is very exciting, okay? Because if we could show that that summatory expression actually does converge to the integral that it appears to resemble, then that means it's going to 0. And that's the thing that we're trying to prove. Can we do that? Well, we'll talk more about it in the next video.